In earlier tapes in this series, we looked at fundamentals of protection and different types of protective relays. We also studied fault characteristics and their effect upon the power system. Now, in this videotape, we're going to go into more detail and discuss protection schemes specifically for power generators. As we are well aware, generators are built in an extremely wide range of sizes, depending very much upon the application and the particular type of prime mover. For example, we may have a 500 kVA diesel-driven generator, which acts as standby for essential auxiliary services. We may see a 10 megawatt gas turbine-driven generator, which is used for quick start emergency standby on the power system. Or we may encounter a steam turbine-driven 30 megawatt generator used in an industrial installation, such as a pulp and paper manufacturing process. The majority of generators installed by power companies to feed into the power system are in the range of 200 to 500 megawatts. And generally, these are driven by steam turbines or water-powered hydraulic turbines. In some instances, we may encounter two separate generators coupled together electrically and also through the turbine steam path. The compound turbine cylinders are arranged in series as far as steam flow is concerned. Another arrangement has two generators in tandem driven by the same turbine. And in yet another method, the radial type turbine drives a generator on either side. Clearly, the electrical coupling of these generators requires special consideration. When considering protection of the generator, we must not forget the prime mover. For example, suppose an insulation failure occurred to the winding inside this generator. It would not be sufficient just to trip out the main breaker and disconnect the unit from the electrical system. We would also need to trip the stop valves and shut down the prime mover so as to prevent further damage. Similarly, if a problem occurs within the prime mover, which necessitates tripping the unit, intertrips must be provided to trip out the generator breaker as well. As this tape deals specifically with generator protection, we will not be discussing prime mover problems or protection schemes. Indeed, this subject is very well covered in others of our video programs. When a generator is tripped from the system, its excitation system must also be de-energized by tripping the field breaker or equivalent. There are two basic methods of connecting the generator to the power system. Smaller generators are generally connected through the circuit breaker directly to a common bus. Several other generators may also be connected to this bus. The bus feeds the power system and also supplies the station service transformer, which provides power for the station auxiliaries. A fault occurring internally on generator 1 should be detected by its protection system, and this will cause its specific breaker to open and its own excitation system to de-energize. Now, on large generators, the terminal voltage, which may be, say, 13.8 to 25 kV, is stepped up by its own unit transformer to 132 kV or higher before feeding into the bus. The generator breaker is located after the delta Y unit transformer. The advantage here is that the breaker is used to interrupt a lower current than would be the case if the breaker were on the primary side. Note that any fault occurring inside the generator will open this breaker and so isolate the transformer as well. In this arrangement, it is usual to connect another transformer to supply auxiliary power. This unit station service transformer, which is connected directly to the generator terminals, feeds the unit auxiliaries. The unit auxiliary bus has an alternative feed from a general station service transformer, as the unit auxiliaries need to be energized during startup. However, once the unit is synchronized and online, this breaker will be closed and the general service breaker opened. Now, in this situation, in the case of an internal fault developing inside the generator, both the main circuit breaker and also the auxiliary circuit breaker must be opened so as to completely isolate the generator. It is normal to provide a throw-over arrangement so that the general service breaker will be closed automatically to continue to feed auxiliaries. As before, the field excitation system must be de-energized whenever the unit is tripped. The three separate phase windings of the generator are located around the stator to provide the correct angular phase displacement. Diagrammatically, the three phase windings are often shown like this. In practice, both ends of each phase winding are brought to a common terminal block. The 6 insulated bushings are usually located beneath the generator. On large generators, CTs are located in all 6 bushings. This convenient arrangement enables us to connect the phase windings in either delta or Y according to system voltage requirements. The most common connection, Y, would look like this. The beginning of each winding, A1, B1, and C1, are all solidly connected together, and this neutral point may then be connected to ground, usually through an impedance. The other end of each winding, A2, B2, and C2, provides the three-phase output from the generator. Diagrammatically, this Y connection is commonly shown like this. A1, B1, and C1 are connected together to form the neutral, and A2, B2, and C2 are connected to the power system. And here we see the terminal connections for the delta arrangement. Check through this connection in detail in your workbook. Again, this may be shown diagrammatically like this. Obviously, with the delta arrangement, there can be no common neutral and therefore no connection to ground. Let's now briefly go through the types of problems which can occur on a generator. Certain defects can arise which are mechanical in nature, such as bearing problems, lube oil problems, vibration, hydrogen cooling system problems, high winding temperature, perhaps due to partial insulation failure, prime mover failures or problems. Normally, all of these items are continuously monitored by appropriate measuring devices, and attention is drawn to abnormal conditions by alarms and annunciators. In extreme cases, tripping may be initiated. However, in this video series, we are more interested in generator faults which affect the power system. Hence, we'll focus on this area. Most internal faults in generators are caused by failure of the insulation in the stator winding. This results in a phase-to-phase short circuit or phase-to-ground fault. An arc will rapidly develop with possible catastrophic heavy damage to the stator windings and also the stator laminations. A complete rebuild may be necessary. It is essential that the generator be isolated from the system immediately and the prime mover stopped as soon as the fault is detected. Another type of internal fault is the ground fault on the rotor, that is, the field windings. Now, this is not such a serious problem as the rotor operates at a relatively low DC voltage, about 500 volts, compared with the stator winding voltage of, say, 15 kV or more. Moreover, the rotor winding is ungrounded, so there is no path for flow of ground fault current. For this reason, a ground fault on the rotor will not call for immediate tripping, but rather the need to schedule a convenient outage for inspection of the generator. We'll be looking at rotor ground detection later in this tape. Yet another internal fault could cause the failure of excitation altogether. This could provide a serious upset to the power system as it attempts to supply the excitation current through the stator windings. We'll be talking about this and other faults in more detail later in this tape. Other possible abnormalities may be due to system conditions such as excessive stator current. This results in overheating of the stator windings. Overvoltage, which may damage insulation. Underfrequency, which may damage the turbine blades due to vibration. Motoring of the generator due to loss of the prime mover. This could result in overheating and consequent damage of the low-pressure turbine blades. Unbalanced currents in the generator stator due to serious system unbalance. This will cause overheating of the generator rotor due to negative sequence components. Loss of synchronism. If the unit falls out of step with the system, this could cause the rotor to slip a pole. Closing the generator breaker with the generator out of phase with the system. This could cause serious mechanical damage to the generator windings and the turbine. We will be looking at all of these items in more detail as we go through this tape and discuss the various protection schemes. But first, let's take a break and then we'll come back and look at protection schemes for phase-to-phase faults. For now, please switch off the tape and review this material in your workbook. As we mentioned earlier, the most common generator internal fault is the phase-to-phase or phase-to-ground fault due to failure of winding insulation. For protection against phase-to-phase faults, differential schemes are normally used. You will remember that we discussed the principles of differential protection in an earlier tape. In small generators, one simple way of achieving this is by installing toroidal CTs at the terminals like this. For each phase, there is a separate CT encompassing both ends of the winding. When current flow is normal, the incoming and outgoing current balance out. However, in the case of an internal fault between phases, incoming and outgoing currents will not balance, and the residual will flow in the CT secondary and operate the relay. In this instance, the relay will usually be of the instantaneous overcurrent type. On large generators, it is physically impossible to pass both conductors through the window in the toroidal CT. Therefore, separate CTs are installed at each end of the winding. Here we see a typical differential protection arrangement for a Y-connected generator. Note the polarity of the CT connections. This is vital to ensure the correct direction of current flow in the CT secondaries. When there is no fault and thus no out of balance, no current flows through the operating coils. On the other hand, if a fault occurs, say, between windings A and B, then an out of balance will occur and operate relays A and B. As mentioned before, the CTs are usually located in the bushings at the generator terminals. If the generator is delta connected, then the differential CTs would be connected like this. Now, this arrangement is a little more difficult to follow, so make sure you spend time on this diagram when you study your workbook. Note that the outboard CTs are connected in Y. This is important to the operation of the relay. When no fault exists, the sum of the secondary currents, IA, IB, and IC, is equal to 0, and therefore no current flows in the neutral. If a fault does occur in the generator, there will be out of balance, and secondary current will flow in the neutral to operate the relay. To provide sensitive differential protection to generators, The CTs should be of the same type and manufacture, and preferably the same ratios. Also, it is preferable not to connect any other equipment to the CTs so as to keep the burden low and so increase the accuracy of the protection. Usually, for generator protection, the restraint coils are set low, that is, to 10 or 15% differential, in order to provide high sensitivity. The pickup current of the relay is also set quite low, between, say, 0.15 to 0.5 amps. When the relay operates, it will immediately open the main circuit breaker, de-energize the field, and initiate shutdown of the prime mover. On large generators, a split winding is sometimes employed. This means that for each individual phase, there are two windings in parallel, like this. Of course, differential protection will be provided across the generator in the conventional way. However, this will not be able to detect insulation failure between windings in the same phase, because the current entering and leaving that phase is still in balance. Even an open circuit in one of the pair of windings would go undetected. Only when the fault develops into a major phase or ground fault will the differential scheme operate. As most insulation failures do commence in a small way, it is advantageous to detect the problem early. And for this reason, additional differential protection may be installed like this. Additional CTs must be available in one of the halves of each phase winding. This, in turn, is compared with the total value of current in that phase. The CT ratios must be selected accordingly. Operation of this relay may be connected to provide alarm to the operator instead of tripping the unit, and so provide time to arrange an outage for inspection of the unit. On a single line diagram, the differential protection of the generator would be shown like this. Operation of the 87G relay trips both the main and auxiliary breaker. It also trips excitation and the prime mover. But look, the generator terminals are solidly connected to the primary of the unit transformer. So the generator must also be tripped in the event of a transformer fault. Normally, differential protection is installed across the transformer, 87T in this case. The same thing goes for the unit service transformer. Here once again, separate differential protection, 87ST, is connected across this transformer. It is also quite common to add further differential protection by linking CTs across all three items of equipment. That is, the generator, the unit transformer, and the unit service transformer. We can call this 87TG. Operation of any one of these differential circuits will trip the main breaker and associated equipment. For a small generator which is connected directly to the bus, the arrangement is much simpler. Here we see the 87G differential relay connected across the generator, and the circuit includes the generator breaker. Outboard CTs are usually located in the breaker bushings. Now, we have many other protective relays to add to these diagrams as we go along. In the next segment, we'll be talking about phase-to-ground faults. But for now, let's take a break. Please switch off the tape and review this material in your workbook. You'll remember in an earlier tape that we discussed grounding. Large generators are normally grounded through a high impedance in order to limit the value of fault current to under 10 amps. This limits the amount of internal damage that can be done to the generator by the flow of fault current. Ground fault current will flow from the faulty winding to the stator laminations, then to the frame, which is connected to the grounding mat. From here, it will flow up the generator neutral, so completing the path for circulation. A CT can be connected into the neutral to measure this flow of current. The CT secondary will be connected to a time over current ground relay, device number 51G. More commonly used, however, is an inverse time over voltage relay set to pick up at about 10 volts. Instead of a resistance, the impedance in the neutral will be provided by a transformer, the secondary of which is connected to the 59G relay. The grounding resistor is connected in the secondary circuit and sized typically between 100 and 200 ohms to limit the magnitude of fault current flowing through the neutral to 10 amps or less. This relay will operate for ground faults occurring in the generator, the primary of the unit step-up transformer, the primary of the unit station service transformer, and the interconnections. As previously discussed, a ground fault on the system would not normally be felt in the generator circuit. However, in certain situations, a ground fault may be felt due to capacitive coupling of the unit transformer windings. Therefore, operation of the sensitive 59G relay must be delayed to permit the fault to be cleared by primary protection on the transmission system. Quite often in this ground protection arrangement, a CT is installed in the secondary circuit, and this operates an instantaneous overcurrent relay to provide backup for the overvoltage relay. In many generators, some third harmonic current flows through the neutral under normal operating conditions. This is because the generated sine wave is not perfect, perhaps due to the design of the generator itself, or more likely, the loads which are being imposed upon the generator. The ground fault relays must be isolated from these third harmonic components in order to prevent inadvertent tripping. This is usually achieved by a tuned circuit in the relay itself, which blocks these components. In contrast to this, we may often encounter an undervoltage relay, 27G, which functions using the third harmonic. This relay is connected in parallel with the time over voltage relay, 59G, and it is tuned to respond only to third harmonic currents and voltage. Under normal operation, where third harmonic voltage is present, this relay does not operate. Remember, it is an undervoltage relay. However, if a ground fault occurs in the generator windings close to the neutral, then these third harmonic components will be short-circuited, and the corresponding third harmonic voltage will be considerably reduced, thus operating the relay. But why is this necessary? We already have ground protection in the form of the 59G overvoltage relay. We also have, quite often, backup in the form of an instantaneous or time over current relay in the secondary circuit. And now we have yet another. Well, the reason is that when an impedance is inserted in the generator neutral, 5 to 10% of the winding will be unprotected. If a ground fault occurs within the winding close to the neutral, the generated voltage at this point will be so low that the amount of fault current in circulation will probably be insufficient to operate the relays. The addition of the third harmonic undervoltage relay helps protect this first part of the winding. We've been discussing ground protection for the large unit type generators found in most utility systems. Now, let's take a look at the smaller generators which are connected directly to the bus. This is often the case in industrial generating plants. Where several generators are connected to the same bus, an economy is often realized by installing one single common grounding connection. In this example, it is connected on the bus. This means that if any particular generator is out of service, or if it is tripped, there still will be a ground for the remaining generators. But this does provide a selectivity problem. For example, if a ground fault occurs on generator 1, the fault current will flow up the common neutral as before, but a simple overcurrent or overvoltage relay fitted here would not know which particular generator to trip. We can get over this problem by installing a ground differential relay on each unit. The 87GD has two operating coils, one fed from the differential CTs of that particular generator, and the other from the common neutral CT. We'll call these, respectively, the differential coil and the neutral coil. In order to trip, the two currents must be in the same direction. Now, let's look at the situation when a ground fault occurs on the winding of generator number 1. Current will flow in the common neutral, and this in turn will energize the neutral coil in each of the ground differential relays. Let's look at generator number 2. Current flowing out from the generator will be out of balance to feed the fault, and so a differential current will flow in the CT secondary. However, if we look carefully, we see that the current in the differential coil is in the opposite direction to that in the neutral coil, thus preventing this relay from operating. In other words, the differential component acts as a permissive for the neutral component. Now let's look at generator number 1, which contains the fault. Here the current is flowing into the generator to feed the fault. In this situation, the out-of-balance current in the differential circuit assists the neutral current and so permits the relay to operate and trip this breaker, removing the faulty generator from the system. We earlier mentioned compound or tandem generators, which are driven by the same prime mover system. Where the two generators are connected to a common unit step-up transformer, it is usual to ground only one generator neutral and install ground protection here. In case of a fault on either generator, both units will be tripped by the single protection. In some installations, the generators are connected to two separate delta primaries of a three-winding transformer. In this case, both generators need to be separately grounded, and each provided with separate primary protection. Of course, a fault on either generator will cause a shutdown of the common prime mover and both generators. Now, at this point, let's take a break, and then we'll come back and look at backup protection and additional protection devices. For now, please switch off the tape and thoroughly review this material in your workbook. So far, we have focused our attention on phase-to-phase faults and phase-to-ground faults. As we pointed out, these are by far the most common generator faults. Now, in this segment, we will look at other types of protection, including backup protection. First, let's look at the small, directly connected generator. Here we see the 87G differential relay connected across the generator. We have ground overcurrent protection 51G. We could also have ground protection provided by a ground differential 87GD, as discussed in the last section. For backup protection, a CT located on the generator output conductors supplies secondary current for several different relays. We see here a negative sequence relay, a voltage restraint overcurrent relay, a directional power relay, and a field relay. Notice that several of these relays are provided with voltage from a VT in the generator output, in addition to current. Let's take a closer look at the function of these relays. First, the negative sequence relay. We saw in the previous tape that negative sequence currents exist in the system when the phase currents are unbalanced. This occurs with a phase-to-phase system fault and would normally be cleared by line protection. It also occurs with a phase-to-phase generator fault, which is normally cleared by its differential protection. However, if the primary protection fails to operate, then the negative sequence relay will register the continued presence of the negative components and trip the generator accordingly. Hence, it acts as a backup to the primary protection. But the negative sequence relay also has a primary function. That is to prevent overheating of the generator rotor in the case of prolonged out-of-balance operation. We can think of the effect of negative sequence current and voltage as opposing generator rotation, and the consequent braking effect causes overheating of the rotor. This would occur if the load demand on each phase is significantly unbalanced. A typical example of this occurs where an industrial generator may be feeding, say, an electrolytic furnace or other unbalanced loads or lines. The generator designer specifies the negative sequence limit for each particular generator. This limit is, in fact, a combination of current and time. It is proportional to the square of I2, that is, the negative sequence current, times T in seconds. A lower negative sequence current can be tolerated for a much longer time period. The negative sequence relay measures this combination of current and time and is set to alarm or trip the unit to prevent damage. Another backup relay is the 51V. This is a time over current relay with voltage control. It is intended to operate as a backup for the differential relay 87G in the case of an internal fault in the generator. But it is not just sufficient to set this relay to operate at a high current level, because it would then operate for faults out on the power system. In order to make this relay selective, we can take advantage of the fact that when an internal fault occurs on the generator, the terminal voltage falls. When voltage is normal on the system, the voltage restraint element prevents operation of the time over current relay. Conversely, when the voltage falls, typically below 80% of normal, then the voltage restraint is lifted and the relay will operate in case of overcurrent. Determining the overcurrent setting of this relay is quite a complex task because sustained three-phase fault current on the generator is actually less than the maximum load current. How is this? Well, you will note on the generator specification that three values of impedance or reactance are quoted: the subtransient, the transient, and the synchronous. Synchronous reactance is much greater in value. Initially, on occurrence of the fault, the current is extremely high during the subtransient period, as the only impedance is the generator subtransient reactance. After a few cycles, it passes through the transient state and settles down to a lower value, which is determined by the synchronous reactance of the generator. The current element of this relay will probably be set to a value which is less than normal rated current. But of course, operation will be blocked as long as the voltage is normal. Another backup relay typically installed on small generators is the reverse power relay. This relay will operate when power flows into the generator, attempting to drive it as a motor. But how could this occur? Well, a typical example could be the inadvertent closure of the turbine steam control valves during load reduction. In this situation, the turbine is no longer driving the generator, but the generator is still synchronized to the power system and so draws current in an attempt to drive the turbine. This situation can cause serious overheating and damage to the turbine low-pressure blades. Typically, the reverse power relay is set to operate and trip the generator if reverse power flow is more than 0.5% of rated power for 10 seconds or more. Another relay which is quite often installed on small as well as large generators is the loss of field relay. Don't worry about this for the moment. We'll be discussing this problem in more detail in the next segment. So that's the small generator. Now let's move on to look at additional backup protection that is usually installed on large unit-type generators. Having already discussed primary protection schemes, that is, differential protection and ground protection, for clarity, we have not put them on this diagram. This will allow us to concentrate on backup and additional protection. As with the small generator, we see a negative sequence current relay, a loss of field relay, and a time over current relay with voltage restraint. Quite often, this 51V relay is replaced by a distance relay, device number 21, which is set to reach through the generator and through the unit step-up transformer into the system. As this is a backup relay, a timer is included so as to allow coordination with the other relays. The distance relay is fed from VTs on the generator's main terminals and CTs at the neutral end. The distance relay is set to operate at 150 to 200% of generator rated current. Remember, this is an impedance relay. As the terminal voltage falls, so the current trip point will also fall. A special problem that may occur with the large unit generator is flashover of one breaker pole. This can occur where the generator through the breaker is connected to a long high voltage line open at the far end with resultant high capacitance and high voltage. When the breaker is opened at no load, one phase may flash over and maintain capacitive current flow out of the generator. Serious overheating could occur in the stator iron due to the capacitive current, and also in the rotor due to the high negative sequence components. The negative sequence current relay may not respond quickly enough to prevent damage. Usually, a breaker pole failure relay, device 61, is installed where the system configuration makes this type of failure possible. The 61 relay operates by comparing the balance of current in the three phases on the primary side of the unit transformer. The relay will operate if one phase current is low, while either of the other two is high, by a ratio of 1 to 3. When the relay operates, it de-energizes the excitation circuit of the generator. In addition to all of these relays, there are several others which are installed specifically to protect the generator against disturbances occurring out on the power system. We'll be looking at these in the next segment. For now, please switch off the tape and review this material in your workbook. As the generator is synchronized to the power system, it is responsive to disturbances which occur on the system. In some cases, this can prove to be hazardous for the generator or its prime mover. One typical example is that of frequency. Large steam turbines are designed to operate within a very narrow range of speed. That is, with the frequency between 59.5 and 60.5 hertz. High frequency can occur as a result of load rejection, perhaps as a consequence of tripping transmission lines or load feeders. However, the turbine governor will normally control the turbine speed and maintain frequency close to normal. If the governor loses control, the turbine is fitted with an overspeed trip, which is set to operate at 110%, say 66 hertz. Low frequency can occur as a result of system overload. If the turbine generator operates below 59.5 hertz, serious vibration and consequent damage can occur to the large, low-pressure turbine blades. The turbine is permitted to operate at low frequency for very short periods of time only. Between 58.5 and 59.5, the turbine is allowed only 60 minutes total accumulated operating time throughout its life. Between 56.0 and 58.5 hertz, the accumulated time limit is only 10 minutes. Often on a large generator, a frequency relay will be installed to alarm the operator when the frequency deviates beyond specified limits. In practice, in a large interconnected power system, the frequency rarely falls outside normal limits. However, such an extreme situation can occur if the power system becomes disconnected into separate areas or islands, so that each generator or group of generators is supplying its own block of load. In some areas, we will have too much generation available, hence the frequency will rise initially. In other areas, there will be insufficient generation, and if load shedding is not rapidly initiated, the generator will become overloaded. The consequence will be a fall in frequency, a fall in voltage, and a rise in stator current. The voltage regulator will increase excitation on the generator in order to maintain line voltage, and this may lead to overheating in the rotor. To protect the rotor, overcurrent protection is sometimes installed in the excitation circuit, and the relay set to alarm the operator. The stator winding may be protected from overheating by the installation of an extremely inverse time overcurrent relay. This is set to operate just before the stator winding short time thermal limit is reached. To prevent this relay operating during normal operation, a combined instantaneous element is usually connected as a permissive for the time overcurrent contacts. This will prevent operation of the unit below 115% of normal maximum rated current. At the other end of the spectrum, problems can occur when the turbine generator is running up to speed before synchronism. During a cold startup, several hours are required to bring a steam turbine generator unit up to speed. Therefore, the protection devices must be able to operate at reduced frequencies for several hours. As the unit raises speed and the excitation system is energized, the generator voltage may overexcite the unit transformer primary winding. To protect against overvoltage, a voltage per hertz relay is installed to alarm or trip the field breaker. This will operate at about 115% of rated voltage when frequency is normal. At low frequency, the voltage trip point will be proportionally lower. Serious damage can occur to the generator if it is synchronized out of phase, or even worse, if the breaker is inadvertently closed when the unit is on turning gear or running at low speed. In any of these situations, an extremely high current will flow into the generator windings. Protection against this potential hazard is provided by connecting directional time overcurrent relays, one in each phase. For power flow into the generator, this relay, device number 67, will operate and trip. Another type of relay which is often installed is a synchronizing relay. This will not allow the breaker to close unless the phase angle is within a determined range, usually 10 degrees either side of synchronism. Upsets or variations on the power system could seriously affect the excitation of the generator. A typical example is when voltage is very high on the system. This could be due to the capacitive effect of lightly loaded long transmission lines or high voltage cables. In order to reduce this voltage, the generator voltage regulator will reduce the excitation current circulating through the rotor winding. If this reduction in excitation is taken too far, the rotor may not have sufficient magnetic torque to remain in synchronism. It would lose stability and probably slip a pole and then another. This has a most damaging effect on the generator and on the power system itself. Indeed, minimum excitation is one of the limits of generator operation. Other limits are overheating of the stator winding due to overload, and overheating of the rotor winding due to excessive excitation current. The limits of generator operation are usually indicated in the specific unit capability curve. This shows the combination of megawatts and megavars that can be produced by the generator at different power factors. Positive vars refers to vars supplied by the generator. Negative vars are fed into the generator from the power system. From the point of view of the stator winding, the current capacity is indicated by the MVA. This can be drawn as part of a circle with total MVA 180 as the radius. At unity power factor, we can produce 180 megawatts, or within limits, the appropriate combination of reactive and real power. For example, at this point, the power factor is 0.85 lagging, and the unit is delivering 153 megawatts and 94.8 megavars. However, we cannot maintain the same MVA at lower power factor because another limitation enters the picture. This is the temperature of the rotor winding. In order to keep within the rotor excitation limits, we must keep megavars within this area. Clearly, as the lagging power factor falls, the total MVA available must be reduced. In other words, the capability of the generator is reduced at low lagging power factor. On the leading power factor side, we have another limitation. This is the steady state stability that we just mentioned. There is yet another limit beyond this. That is the overheating of stator iron, which results from excessive flow of capacitive currents. Usually, the excitation system is fitted with a limiting device so as to prevent reduction of excitation to a dangerous level. But what would happen if the generator did suffer a complete loss of field, perhaps due to a defect in the excitation circuit? In this situation, remember, the generator is still connected to the power system and still delivering megawatts because it is still being driven by its prime mover. However, it will no longer supply vars. On the contrary, it will draw vars from the system in order to maintain excitation. The power factor will move to, say, 0.5 leading. So the generator will continue running and producing power as an induction generator. However, this will probably lead to low voltage at the generator terminals, and more important, serious overheating will occur in the stator iron. If the field cannot be restored promptly, the unit should be shut down. Normally, protection relays are installed to detect reduction or loss of excitation. These relays may be used for alarm purposes, but more often they initiate tripping of the unit. Earlier loss of field relays worked by measuring current in the excitation circuit. When this fell below a preset level, the relay operated after a time delay. Nowadays, loss of field is detected by measurement on the generator high voltage side. One method is to use a megavar meter set to operate when the imported, that is, negative megavars reach a high level, implying that the unit is operating as an induction generator. The preferred method is to install an impedance relay, which compares the state of voltage and current. During normal, full load operation, the impedance will be out here. A short circuit on the generator terminals will bring the impedance to this point. However, if a loss of field occurs, the measured impedance would move usually into the third quadrant due to the import of reactive power. Consequently, the loss of field impedance relay is set to operate in this zone. While speaking of excitation, one other area that requires protection is a ground fault on the rotor or excitation system. As the excitation system is not normally connected to ground at any point, a ground fault does not require immediate tripping of the unit. However, it is advisable to arrange an outage of the unit for inspection as soon as possible, so as to avoid damage which could occur in the case of a second ground fault occurring. Two grounds on the rotor would effectively short out some of the winding and distort the flux path. Serious mechanical damage could occur to the rotor. A ground fault detection system is shown in your workbook. You may come across the term subsynchronous oscillation in your work. What's this? Well, this complex problem may occur in rare instances where the generator is connected to a long EHV line, which has series capacitors in the line to compensate for line inductance. The effect of these capacitors is to raise the natural resonant frequency of the line close to the synchronous frequency of the generator. As a result, some oscillation is set up in the generator. This gives rise to overheating in the generator and may even lead to mechanical damage due to oscillating torque on the shaft. A special relay is sometimes installed to detect this condition. Throughout this videotape, we have presented the general types of protection devices installed on small and large generators. Let's briefly summarize the relays that we have mentioned. This list is included in your workbook. First, primary protection, generator differential, unit step-up transformer differential, unit service transformer differential, unit differential, ground differential relay, time over voltage ground relay, third harmonic under voltage relay, loss of field relay. And here we have the commonly employed backup relays, negative sequence relay, impedance relay, reverse power relay, time over current ground relay, time over current relay with instantaneous element, over current relay with voltage restraint, directional current relay, breaker pole failure relay, and voltage per hertz relay. Not all of the generators in your company will have all of these devices installed. You may also come across other protection devices which we haven't mentioned. But now that you have a knowledge of what is available, make sure that you check your own generating units to ascertain the type of protection relays that are installed and their settings. Also, remember to locate the CTs and VTs which provide information to these relays. You should also discuss with your colleagues and rationalize why such protection devices are installed on particular units. At this point, please switch off the tape and thoroughly review this material in your workbook.